the nodal voltages V1, V2, and V3 using nodal analysis technique. This is a typical exam problem that I give to my students in previous semesters whenever I teach the circuit analysis course. And the reason is that we're gonna see a couple of dependent sources here. So those dependent sources are kind of cumbersome to many of the students, yet those are important models, especially when we have to deal with electronics and amplifier designs, that those models are extremely important. So I stress those models in the lower division courses, especially early on in the semester, because the more you see those models, the more comfortable you become in using those models, the better chances that you will be comfortable in dealing with advanced electronics in later semesters. So this is a particular circuit where we have a couple of dependent sources in the circuit. And if you look into the first one is a voltage source. So you need to recognize that this is a voltage source because we have polarities here. And the second one is actually a current source, and we know that it's a current source because it has an arrow inside it. The arrow indicates the direction of the current which is going into the node V1. So because in this circuit we are dealing with nodal analysis and we want to solve for V1, V2, and V3, then we need also to express the dependent parameters. Those are Vx and Ix in terms of those nodal voltages. So at this point, this should be trivial to you that this voltage here is 20 volts. Those are the unknown nodal voltages. And this is the reference node, which is the 0 volts node. Before we do anything, we need to define Vx in terms of the nodal voltages. So we're going to look at the circuit and we're going to see where is Vx is located at. So we will see that Vx is located over here, where the plus polarity of Vx is placed at the node V2 and the negative polarity is placed at the side where it's V3. Right? You just follow the polarity, and you can use KVL if you want it, but we say that if you use that a couple of times, then you know that Vx going to be the voltage, the nodal voltage at the plus polarity minus the nodal voltage at the negative polarity. So we can state that over here, that Vx will equal to V2 minus V3. Also, we have another dependent parameter that is called Ix, which defines this current source. So we need to look at Ix in the circuit, and Ix going to be located over here. This is Ix. So Ix is the current flowing from the 20 volts node to V1. Then using Ohm's law, we can easily state that Ix will equal to 20 minus V1 over 1K. It's basically the voltage at this node, which is 20 volts, minus V1, which is the voltage at this node. This is going to give you the voltage across this resistor, divided by the resistance itself, which is divided by the 1K. So all what we did so far is we found Vx and Ix in terms of the nodal voltages V1, V2, and V3. That's what we have over here. Now this is extremely important step when it comes to nodal analysis. Always define those dependent parameters in terms of the nodal voltages. So this is the first trick in the problem, is we have two dependent sources and we need to define those dependent parameters, the Vx and Ix, in terms of the nodal voltages. The second trick in the problem is that if you're gonna look into this voltage source, this dependent voltage source is connected between V1 and V2. So whenever we have a voltage source between two nodes, whether it is dependent or independent voltage source, then we must use the supernode equations for this particular node. So we have to combine the two nodes as a one closed surface, where the sum of the currents leaving this closed surface will be 0. So we're going to use the supernode equations to find or to express the KCL and the KVL for the supernode. So we know that the supernode has two equations. The first equation will tell us what's the voltage difference across the supernode, and the second equation going to sum the currents leaving the supernode to be zero. So if we look into the first equation, we have to follow the polarities of the voltage source. We know that the plus polarity of this voltage source is located at V2 and the negative polarity is located at V1. Then clearly you're going to say that V2 minus V1 will equal to this voltage source, but this voltage source will equal to 2 times Vx. So we can state that V2 minus V1 will equal to 2 times Vx. V2 minus V1 is written here to equal to 2 times Vx. But we already know what Vx is. It's basically the voltage defined here, right? Then this will equal to 2 times V2 minus 2 times V3. Basically, we substituted for Vx here. So now we're going to bring the 2 times V2 to the other side. It becomes negative 2 times V2. And the negative 2 times V3 to the other side, it becomes plus 2 times V3. So when we write the equation, basically it's going to be minus V1, that's the first term. And then we're going to have the V2 minus 2 times V2 becomes minus V2. And the negative 2 times V3, when we take it to the other side, becomes plus 2 times V3. The sum will equal to 0. This is the first equation of the supernode that we have. Now we're going to sum the currents leaving the supernode to equal to 0. Now keep in mind that when you do the supernode, whenever you are at the V1 side, you're going to use V1 as a nodal voltage. Whenever you are at the V2 side, you're going to use the V2 as the nodal voltage. And you're going to sum all the currents leaving the supernode equals 0. So I'm going to start at this branch. So I'm going to say that V1 minus 20 over 1K. So it's going to be V1 minus 20 over 1K. Then we're going to say that the current leaving this branch, so we know that the current going in is 0.5 Ix, then the current leaving going to be minus 0.5 times Ix. Then we're going to go to the other side here, and on the other side we're going to have V2, so we're going to have V2 over the 2K, that's going to be plus the current leaving here, which is plus V2 over the 2K, that's what we have here. And then we're going to say that plus V2 minus V3 over the 4K, which is the current leaving this resistor. So that's what we have, and that's will equal to 0. Now all what we have to do is we need to substitute for Ix here. We know what Ix is. This is Ix is 20 minus V1 over 1K. We're going to substitute for it here. So we will keep everything the same. We're going to only come to this portion and substitute for Ix. So here I will have V1 minus 20 over 1K. Over here I will have minus 0.5 times Ix, which is that value here, 20 minus V1 over 1K. Then we're going to have the plus V2 over 2K, and then the plus V2 minus V3 over 4K. The sum will equal 0. We're going to get rid of the 1Ks here. Basically we're going to multiply by 1K in both sides of the equation, so the 1Ks will cancel out. And then once we do that, we're going to group the V1 and the V2 and the V3 terms and move the other numbers to the other side. So for the V1 here, I will have 1, and then minus the minus going to be plus. So I'm going to have minus 0.5 times the minus 1, so it's going to be plus 0.5. That's times V1. And then for the V2, I will have 1/2, which is V2 over 2. Plus V2 over 4, so I will have 1/2 plus 1/4. And then for the V3 I will have minus 1 over 4, and that will take the other numbers to the other side. So here I will have minus 20, we'll go to the other side, will be plus 20, and here I have minus 20 times 0.5, so take it to the other side, will be plus the 20 times 0.5. Now we can simplify this equation and make it look nice and clean. So over here we're going to have 1.5 times V1, and for the V2 term I will have 0.75 times V2, and for the V3 term I will have minus 0.25, and this will equal to 30. 20 plus 10 is 30. So this is the second equation of the supernode. So we sum the currents leaving the supernode equals 0. That's what we have. And now we're going to move to V3. So we're going to sum the currents leaving V3 equals 0. So we're going to start with the current leaving this particular resistor. So it's going to be V3 minus V2 over 4K. So we have V3 minus V2 over 4K. Then the current leaving this resistor going to be V3 over 2K. And finally the current leaving this current source is going to be minus 5 milliamps. This will equal to 0. So now we're going to multiply the both sides of the equation by 1K. When we multiply by 1K, the K's will cancel at the bottom, and when we multiply the milli by 1K, they cancel out. So basically those terms will disappear, and now we can clean this equation. So we're gonna start with the V2 term. So we're gonna have negative 0.25 times V2, and then for the V3 term we're gonna have 1 over 4 plus 1/2, which is plus 0.75 times V3, and we're going to take the negative 5 to the other side of the equation, will be plus 5. So this is the third equation that we have. And now we can express those equations in the matrix form. So that's what we're going to have, those equations in the matrix form, and then solve for the three equations, three unknowns, and we're going to have V1 will equal to negative 10 volts, V2 will equal to 70 volts, and V3 will equal to 30 volts. So this is a very good problem. It's a typical exam problem in my class where I ask you to solve for the nodal voltages. You have a super node and you have two dependent sources in the circuit. And usually I will ask you to solve for a current somewhere in the circuit also. So once you solved for the nodal voltages, I might ask you to solve for the current here, and I might ask you for the power delivered or absorbed by any of those elements that we have. You need to check if the element is passive or active, whether it is absorbing or delivering power. But this is a typical nodal analysis example that I like. It's not the hardest example, but it requires some thinking, and it shows if the student can apply